So the goal of this video is to step through a process of doing a semantic segmentation on geospatial data using open source and or free software tools. So this example specifically, we're going to rely on PyTorch as implemented in Python, along with some different R environments. So we're going to do a lot of the data prep and data cleaning and data and model evaluation using R, and then do our modeling and inference using PyTorch and Python. So I'm going to step through each of the scripts that are used to do this work, just so if you want to try to do something similar, work through our process, or adapt our scripts for another task, that you can do that. Okay, so all these examples are hosted on this West Virginia View Geodal examples site, and then within here we're going to develop several different examples. The one we're looking at here specifically is in this TopoDL UNet PyTorch folder, and you can see a series of scripts here. We have some Python scripts, .py, and then some R scripts with the .r there. Okay, so before we get into actually working through the example, I wanted to just describe what it is that we're trying to actually do here. Okay, so this data was taken from this manuscript. Make this a little bit bigger here. So with semantic segmentation deep learning for extracting surface mining extents from historic topo maps. So if you're not familiar with topo maps, in the United States we have a series of topographic maps at different scales that represent, obviously topography and then different thematic features. One type of feature that is represented on historic topo maps is surface disturbance. So here in West Virginia, that's generally associated with surface coal mining. And generally that's shown as this pink blotchy pattern. So this is a wealth of historic landscape information, but unfortunately, it's not readily available as vector data. So if we wanted to actually use this data in some type of analysis, we would need to actually generate vector objects or boundaries from it. So in this task, our goal is to effectively train a semantic segmentation UNet deep learning algorithm how to recognize this pattern from topo maps and extract the extent of historic topographic features. Note that we had an example that used this same data, but we implemented it all in ArcGIS Pro. This is similar, except now we're going to implement it using some open environments. Note that the data for this comes from the United States Geological Survey, all the historic topo maps, and the training data have also were also originally created or digitized by the U.S. Geological Survey, where users went through and hand digitized the extent of these features to create a training set. Okay, so if you want to follow along with this, we made the data available on the West Virginia View website, so let's go to that. Okay, so on the West Virginia View website, if you go to Research, under Datasets and Tools, there are a couple links here. This dataset is this TopoDL, and that'll download a folder. I think it's a couple gigabytes. And then once that's downloaded, you're going to get a folder a zipped file. It's like 2.2 gigabytes there, called topodldata.zip, and you're going to need to uncompress that. So when we uncompress it, we end up with this. Sorry, that's the wrong one. This folder here, and in there we have some different examples for Ohio, Virginia, and Kentucky. In this example, I'm mainly just going to work with data from Kentucky. I'm not going to really use the Virginia or Ohio data, but they're there if you want to test model generalization to new geographic extents or topographic maps that might be a little different than the ones that the model was trained on. So for each of the state data sets, there are 3 folders. The mines folder, these are shape files representing the extent of surface mining for each topo map. The quads is a rectangular extent of each quad, which we are going to use for masking. And then we have the topo maps, which are represented here as geotiffs. So if you want to see that data, let me open that up in QGIS here. This is an example. This is the Offet quad. This is data from 1954. So again, we just turning things off here. This is the topo map, which is a georeferenced raster dataset, RGB. And again, you can see in this specific example, there's a good bit of mining there. And then we also have these, which represent the extent of surface mining, and that's what we're going to develop our training data from. And then lastly, we have just an extent. So note these topo maps have caller information, or this ancillary information around the actual map frame. And we don't really need to work with that or classify it. So we're going to need to remove it. So we'll work through that in our process. Okay, all right. So I think we're ready to get started. So I'm going to work in R Studio, which is an IDE for R, but you can also work with and use Python scripts. Okay, so I'm just going to start from a scratch with a new project. So we're going to go to open. We're going to open up R Studio here. I guess let's do it here, and I'm going to open a new I'm going to create a new project. So I'm going to do new project. And in a second here, it should let us launch that new project. Maybe. There we go. All right, so I'm going to do new directory, new project, and this is the topo works. I'm going to call this, we'll just call it topo for video. Create project. All right, so that should open up a new blank project. So now we want to actually start working. So again, I already made all the scripts, so we're not going to sit here and write scripts from scratch. I'm just going to step you through them. It would take too long if we started from scratch. Okay, so we want to open some files first. So I'm going to go into the scripts folder, which houses the files that are the same ones that are on the GitHub repo. So first thing I'm going to do is open up this prep.py and R file. Okay, so if you are going to work, if you're going to want to link R and Python, you want to run Python code from RStudio, you're going to need to work with the reticulate package. So what I'm doing here is I'm loading in that library. Actually, let's make this, let's step up the font here so you can see it a little bit better. There we go. Okay, so here I'm loading in that library, which has already been installed. And then I'm pointing it at a specific Python environment. And this Python environment I set up, and I showed the setup in another video. This is an environment that has all the tools we need to do geospatial deep learning with PyTorch, including some like geospatial libraries like GeoPandas and Rasterize and whatnot. And then if we call pyconfig there, we can see the configuration. Okay, so let me just run this so we can see what we get. Okay, cool. So again, I set it to my Python virtual environment that I was interested in, specifically the Python file in that environment. And then calling pyconfig shows us what Python we're using, the lib file there, the home directory, and then also it tells you what numpy you have set up. So let's see here, I got numpy 1.2.2. Okay, so, or 1.20.2. All right, so that should allow us to use Python and R in RStudio, and also the specific environment that has all the libraries that we need. Okay, so the first thing we need to do is some data prep. So if we go back to QGIS here, you can see that we have some raster files and we have some polygon boundaries. But what we want is some raster mass representing our classes. Basically, background is 0, 1 is mining. And we also would like to clip down these images so we're only dealing with the map extent as opposed to having the caller information. Okay, so let's look at that first. So I'm going to go in here and open up a couple more files. So we're going to open up this, let's see, which one do we need? Make masks file. And and then also I'm going to open up this topo data prep R file. Okay, so let's look at this mask file first here. Well, actually, sorry, let's look at the topo data prep first. All right, so remember, if you're doing deep learning, you generally want to partition your data into separate sets so that you can train and then validate the models without, some bias, right? Because these models are known for having issues of things like overfitting. All right, so what I'm going to do to begin with, and I'm going to run some of this code because it doesn't take very long. So we're going to call in some libraries that we need. So we're using dplyr, which is one of the tidyverse libraries, and we're using that for data manipulation. Then string R, which is used for string manipulation, working with strings or characters. Terra, if you're not familiar with Terra, this is the recent replacement for raster, and I found it to be a lot faster, so that's why we're using it here as opposed to the raster package, which is what we traditionally use for dealing with raster, geospatial data in R. And then imgur here, or imager, allows you to work with image data, like non-geospatial image data, just like pictures. Okay, so we're going to list out all the files that are in these directories. So I'm looking at specifically, oh, actually, sorry, I'm looking at the wrong one. We need to go into make mask first. Sorry about that. I was right the first time. Okay, so this is after we make the mask. So the first part here is make masks. So this is where we're going to create our raster masks from our vector data, so the shapefile of the mine boundaries. And then also we want to clip down the raster, so we don't have the collar information. Same inputs, libraries though. Okay, so to do that, I'm creating a function. So I'm going to create a function called make masks. Again, we call the function there, which is telling us that we're going to define a function. And these are all the parameters that the function can accept. So it's going to accept an input image, input features, which are going to represent your features of interest, whether or not you want to crop the features. Then we have this extent argument, which is a mask. What field in the vector layer differentiates each class, or we can just use a constant. The value to use for background, and then the output image and the output mask. And then there'll be a mode, which we're going to use both mode here. Okay, so what's this actually going to do? Okay, so first thing it's going to do is it's going to accept the path to the image, and it's going to read that image in. Note here I'm using this clamp function, which is from Terra. I found that sometimes if the data are scaled from 0 to 255, it'll freak out because there's like no value left for no data assignment. I don't know if it's a GDAL issue or something. So this clamp basically takes, it scales the data from 0 to 254. So if one of the pixel values is 255, it's just going to turn it into 254. So we have an extra value left over to use for no data if we need it. That was just an issue I ran into when I was making this. I don't know. I wasn't sure what the exact cause was, but this seemed to fix it. And this is 8-bit unsigned data. Okay, and then we use the vect argument or vect function. Again, this is coming from raster to read in the vector features. All right, so then we make sure that the features and the raster data have the same map projection, just using the project function. So I'm basically reprojecting the features to the same projection as the raster data. Now, you could do it the other way around, but I generally found that R is faster at manipulating projections for vectors than it is for raster, so that's why I'm manipulating the vector as opposed to the raster. Okay, and then if crop is set to true, then I'm going to also read in an extent object. Again, if we go back here to QGIS, that's going to be this boundary. And then I make sure that the projection of the extent matches the projection of the raster data, and then I crop down the image within that extent. Okay, and then the next step is to rasterize the features. So here we're using the rasterize function. Again, this is from Terra. So this is our reprojected features. We're going to have it take on the same spatial extent as the image data. The field value is going to be equal to whatever field, the value is going to be equal to the field argument, and then the background is the background argument. And then we have a couple different modes. So if we want to just get the mask, then we would use just mask mode. But we want to create copies of the images and create raster masks because of the cropping issue. So we're going to write out both the image and the mask. Okay, and then if you don't provide a valid mode, either both are masked, then it'll get flag an error and stop there. Okay, so once we have that function called, so I'm just gonna read this in here so we can see it. Once that function is created, so you can see it's here in our list now, then we can run it. But instead of just running this on one image, we want to be able to run it on all of our topo maps from the KY or Kentucky dataset. So to do that, I use this list files function. This is base R stuff. So I give it a directory, and then I say I don't want the full names, so it's just going to give back the file name, not the full path. And I'm just going to basically pull anything that ends in TIFF. So it'll pull all of our TIFF files. So if I run that, I should get a list of all the topo maps that are in my folder. So there's 122 topo maps in there, as you can see listed out here. All right, and then the next step is I go through and create a data frame that has this image column in it, and I basically just get rid of the file extension. That's what this substring does. So I'm reading in the image, and I'm reading, and it's going to pull 1 through the number of characters minus 4. So .tiff, that's 4 characters, right? So I'm just pulling off the file extension. So we run that, we end up with this. So I have this image column, and I have the file name without the extension on it. Okay, and then I create a couple. I add some fields to this, so I basically append the path to the image, and then the file name, and then the path to the mask and the file name, and then the path to the extent and the file name. And note here I'm adding the extension back on, so .tiff, .shape, .shape. So if we run those, now if we open up this file, now for each feature we have this kind of the generic name, the path name and extension for the image, the math data that are currently vector shape files, and the extent, which is a vector shape file. All right. Okay, and then we set out, I basically create paths to where we want to save the output. So image out and mask out, so basically I'm saving it to this folder. The images go to an image subdirectory, and the mask goes in the mask subdirectory. And then we basically pull in the original name and add on the file extension. Okay, so what we end up with here is a table that has all the paths to the files that we need and the paths to the files that we're going to write out. And each row represents one of the pieces of data. So I'm not going to run this because it takes a while, but this is actually applying it to the data, the make mask function. Okay, so for I in 1 through number rows in image data frame, so this is going to loop through every row in the data frame, where again each row represents one piece of data, or one topo map and its associated vectors. So for each of those rows, I'm going to run my make mask function. The image is going to be read in as image data frame, row whatever you're on, so if it's 1, row 1, and then the image path. The features will be the path to the mask. Here we're doing a crop because we want to clip it down. This is the extent, the path to the extent. we're going to write out, instead of using a field in the attribute column, we're just going to use a constant value since there's only one class. So we're going to write that out to 255 or 254, and then we're going to set background value to 0, and then naming our outputs. So you can see why we made the data frame. I'm effectively using each column in the data frame for each row to specify the required inputs and outputs. So if you run that loop, then it'll spit everything out. I ran this in I think it was under an hour for all the features. Let me show you what this looks like. So if we go back to our working folder, I created this data folder in here, and then there's our image output. So there's all the output. You can see that the border information is now off, and that's because we stripped it off. And we also created these binary masks for each image. So let's open that up in QGIS just to see what we ended up with. So let's go to, let me close this. So we'll go to Data, Image, and let's open up our clipped image. So that's going to be, where is it? This one here. Okay, so let me turn this image off. You can see there's the version of the image clipped down to just the map extent without the color information. And then if we go into the mask, we should be able to pull that same mask object somewhere. Let's see, here it is. So there's a raster version of the mask where 0 or 254 represents the mine class and 0 represents the background or not mining class. Okay, so that's what we ended up with, and so that's already been processed. Again, it takes a couple hours. Alright, so if you remember about one component of deep learning just practically is that you can't feed it entire images or individual pixels. You have to feed it image chips. So the next step is to take these data sets and break them into different sets, so validation, testing, training, and then from those generate a bunch of image chips to train our models on. Okay, so let me open up another file then. Again, this is available in the GitHub. So we want to grab this make masks file. Oh, sorry, I already had that one. We want to grab the chipit file. So this is designed to make chips from larger extents. Okay, so here I'm defining a function. So this is a function called chipit, and it accepts the following parameters. So you give it an input image, an input mask, a number of channels in the image, and these are RGB images, red, green, blue, so 3 channels. The size of each chip, so we're going to do 256 by 256. The stride, so the spacing as it moves between chips. So we set it the same, so 256 and then 256 in the X and Y direction. So what that means is that it's not going to have any overlap between the chips. They're going to be butted up against each other. And then an output directory, and then a mode. Okay, so I built this function to basically accept 3 different modes. So in all mode, it exports all the chips, even if the chips are only background. There's no positive cases in that extent, and it just dumps all those images, chips, and associated masks into 2 separate folders there. So that's all mode. The positive mode, what that does is it only exports out positive cases. So once it makes a chip, it tests to see if there are any positive pixels in it. If not, it just doesn't actually map it or print it. If there is, then it does. And then the last mode, which is what we're actually going to use here, is divided. So what this does is it creates all the positive / background chips and just background chips. It creates all of them, but it partitions them into separate positive and background folders, so you can have 2 kind of separate data sets to draw from. Okay, so those are the 3 modes. What goes on inside of each mode is pretty similar, except for writing out. So let's look at one of these processes. Okay, so before we enter these, so within each mode, the first thing we need to do is from the input image path, we were going to pull that in as a raster. Again, that's using Terra. We'll do the same thing for mask. Note that it's going to want these things to have the exact same extents and projections, which it should because we just generated them with that make mask function, which by default created that. This f name with base name here, what that does is it just pulls out the name of the image without the full path or anything. Okay, and then this dir.create, that creates our directories. So if you don't create a directory structure beforehand, you can have it create it for you. So that'll create these sub image and mask folders inside of your data dump that you're creating. Okay, and then this is a little confusing, but we needed to be able to pull out small extents or arrays out of the larger image. So how that does that is it goes through and calculates beginning points for a series of sequences. So the first thing I do is I get the number of columns in the data set and the number of rows. And then I get the size of each chip, which is an input, that's the size parameter, and the overlap, which is the stride parameter. And then I round up, so this will tell me the number of chips that I need going across and going down. And I round up so I get a whole number of chips, not a partial chip because we want everything to be the same size. And then once we have that, then we figure out the start endpoints of the row and column numbers we need to start each chip. And then we build a sequence from that. So I'm not going to run this because it takes a while, but that's effectively some prep work. And then once that's all defined, it loops through the different column and row start points and pulls out those chips, and then it writes those out to file. And then how it writes it depends on the use case. Okay, so that's what this function does. Okay, so in this topo data prep folder, I actually use that function. Okay, so let's look through that. So the first thing we're going to do is read in our masked and our raster masks and crop down images that we wrote into that data folder. We're going to list those files out, and again, just the TIFF since we're interested in TIFF files. So let's run that. Okay, so here we have a list of 122 images and 122 associated masks. Then I merge that into a single data frame. So if we look at that, oh, it's still thinking. There it goes. So open this up. There we have our image name and mask name, and they should be the same because that's the way we named them. All right. Then I create the full image path and full mask path by just creating two new columns and then putting the path onto the image. Just run that. So now we have four variables here. So we have the name, and then the name with the full path, the mask name, and then the mask with the full path. Okay, and then next I'm using this for loop to take the name and break it into pieces. This is because I want to have some control over the partitioning. So in this data set, there are multiple maps representing multiple dates of the same topo map. And to try to remove any bias in the data partitions, I want every map that is of the same area to end up in the same partition, regardless of the date. So to do that, I first need to have the map name for each map. So if I run this loop, basically what it's going to do is it's going to break the name apart where there's underscores and return those into new columns. So let's run that. Okay, so now if we open up this topo prep, we have where it broke it up into columns. So state, quad name, the ID. So this is scan ID, which is unique identifier, the year, the scale, and then the file extension there on the end. Here I go through and I'm just changing the names of that so that we have nice clean names. So now we just have more usable names set up. Alright, and then we bind all this together, and I define the state name as a factor because we're going to use it as a factor. Okay, so this is input topos 2. We have the image, the mask, the same thing but with the full path, and that here on the end we have all the broken up information. Okay, so next we're going to pull out just the Kentucky data. This actually isn't necessary in this case because I just called in the Kentucky data, but if you had ran all the Ohio, Virginia, and Kentucky maps, you could split them apart this way. but I just did the one set, so we don't really need to do this, but I'm just going to run it so we have the variable name there. So this is going to be the KY topos object here. Okay, and the next thing I do is I pull out a list of all the quad names. So that's this name field. I'm just using name. I'm getting all I'm basically writing all the levels out. Let's run that here. So we open up this quad names, and you can see there are 100 different topo map names. So if you remember, there were 122 files, so that means there are some duplicates in terms of different dates. All right, and then here I'm using dplyr to break it apart. So I'm basically saying that from the list of 100 names, I'm going to select out 70 to be training samples. Then I return the ones that weren't sampled using setDiff. Then I run this process again to pull out half of the remaining ones to be the validation set, and then the remaining will be the test set. Then to each of those subsets, I add a column called select and 1, 2, 3, and then I bind that into the original data set. So let's run all that. Note here I'm using set.seed for reproducibility, so I'd get the same breaks every time I run it. Okay, so let's look at topos combined. That's the output here. That's this one. Okay, so we have the topo name and then whether or not it was selected. So 1, 2, and 3 for their 3 different partitions. And then I join that result back to the KY topos data set using the common name field. So now we have whether or not it was selected, which partition ended up in assigned to each of the features. And then we just break them into 3 data sets. So anything that had a select column of 1 is written to train. If it was 2, written to val, and 3 represented to or mapped to test. So let's run that. Okay, so that created our 3 partitions. And again, we stratified on the quad name so that multiple dates of the same quad ended up in the same partition, which made this selection a little bit more complicated, but I think that's a more robust, statistically valid way to break up your data set. And then here I'm just writing out the val data set to a CSV because we'll use that later. You could also write all these out to CSV just so you have a record. But what we really need isn't each individual map broken into the 3 different partitions. We need to take those partitions and then make chips from them. So here we're going to implement our chip.it function that we made in the other data set to build out chips. And so this is for the training data, the test data, and the validation data. All right, so for the chip.it function, we give it an image, so it's pulling the image path from the data frame. Then it pulls the map path from the data frame. It's 3-channel image. This is our size in stride X, stride Y. This is the output directory, and then we're going to do divided mode. And it's basically the same for each of these, except we give it a different input data frame. Okay, so that takes some time. It took a few hours to run on my machine to create all these chips, so we're not going to run that now, but I'll show you what the output looks like. Okay, so this should be inside of our chips folder, and as you see there, we ended up with our 3 partitions, train, test, and val. So let's look at train. Well, that's big. Let's look at val. And then within each of those, we have our images and our masks. And then within each of those, since we use divided mode, we have our positives and our background. So if you look at the background, you'll see that none of them have any mining extent in them, whereas the positives do. So there's some surface mining there. So now we have 2 separate data sets effectively. Okay, so that's basically it. That would generate, in this chip folder, we have all the masks and image chips we need to train, test, and validate the model. All right, so now we need to switch over and do our modeling inside of Python. So first thing before we do that, we have to list out all of our chips and make CSV files out of those. So I'm going to go back to this prep py and r, and underneath of the configuration here, I've worked through that process. Okay, so I list, what I'm doing here is I'm listing all of the files in all my directories. So my positive images, positive masks, and then positive, 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 and then all the backgrounds for our separate train test and val sets. I take all those and I merge them into a data frame that has the image path and then the mask path. And I do that for the test, train, and val separately, and also for the positive and background separately. So let's just run that and see what we get. So I'm going to run all this. Okay, and then if we look at these objects over here on our list of objects, we should see something that makes sense, hopefully. So our train chips, P, there are 7,771 image chips there, and with 42,071 in the background. So those are a total of 50,000 image chips for training. And then for the validation set, we've got 1,625 positive chips and then 10,201 background. And then lastly, for test, we have 1,246 positive and then 9,446 background. Okay, and then this just writes those out to CSV files, which we can call in and use in our Python code. So I'll show you what that looks like. Those ended up here where I wrote them out. So let's just open the val P one here and pull this over. So we basically have a path to the image chip and then the associated mask chip and then an index field. Okay, so now we're shifting gears to Python. All right, so I'm gonna open up a new file here. So we're gonna open file, and now we want to open up our train Python file. And again, this is our code, so the code's gonna look, Python code, so the code's gonna look a bit different now. Okay, so I have a link here to an example that I use to kind of build around. So there's the link there. Okay, so first thing we need to do is pull in our data, our libraries that we need. And as long as you've set up your environment and you're connected to it, it should pull those in. So I'm pulling in NumPy, Pandas, Matplotlib, OS, CV2, Torch utilities for data sets there, albumations, and then this segmentation models PyTorch library. Let me pull all those in. Now it looks like it failed to load one, so let's see what happened. Okay, I've had this issue before. I'm going to clear this out, and I'm just going to restart my R session. And then I'm going to run this again. It looks like it grabbed the right library, and now let's try to run our imports again. Okay, it worked that time. So I had to restart R there. Not really sure what causes that. Okay, we actually don't need to run this. Here I'm setting some global parameters. So encoder, I'm going to use a ResNet 18 backbone, so I'm setting that. Encoder weights, I'm going to start off with the ImageNet weights. And we only have one class here, which is mine. I don't have to provide the background class. Since this is just a 2 class, we're going to use a sigmoid activation function. And device equals CUDA, this is because we're going to try to run things on the GPU. So we'll run all that. One thing you note in RStudio, when you're running Python code versus running R code, it gives you the 3 cursors there as opposed to 1. Okay, and then this is just some utilities from PyTorch to test and make sure that we have access to our GPU. So this is.available basically says whether or not it's finding a GPU that it can use. Device count is the number of GPUs, and then this is the name of the device. And then I just have a print statement here to print out the results of that. Okay, so yes, we have a GPU available. There's one, and this is it. It's a GeForce RTX 2080 Ti. Note that if you try to do something like this without GPU support, it's going to be super slow or basically not work. So if it doesn't find your GPU, you're going to need to have a look and make sure there's not like an installation issue. All right, so the next thing we're going to do is read in our CSV files of our training and test data. We're going to read in the validation because that's for later, so we're just training and test. And we have our separate positive and background, and we're going to read those into pandas data frames. Okay, so that read in. If you want to, you can check the length. So I'm just going to do length of train P. So remember there were 7,771 of those, so that looks right. All right, and then we want to create one. Well, actually, we don't need to do that. So again, then this just shows you the lengths of those data sets. Oh, sorry, I do need to run this. So I'm concatenating the test, positive, and background into one data frame using the concat function there. Or I guess method. No, function. And then, again, call the lengths. So that should be the same as what we had when we wrote them out. Okay, so there's a couple key components to generating, to working with deep learning and PyTorch. So one of those is to generate a data set. So to do that, we're going to subclass the data set class from PyTorch. And I'm creating a couple different data loader or data sets here. So the first one is seg data train. So that's what we're going to run our segmentation data through. Then we have seg data test, which is we'll use for the test data. And then we'll actually deploy those. Okay, so whenever you create or subclass the data set, there's a couple required methods, like constructor methods, that have to be defined to get to work. So you have to have an init, you have to have a get item, and you have to have a length. So in the init function, this is gonna run whenever the class is initiated. So what we're going to do here is have it read in the positive and background data, which honestly we didn't have to do that here since we're doing it inside of the data set. So this is mainly just so you could see them. So we read that in. There's also options to apply transforms, which we'll look at later. So our transform setup. And then for this case, to deal with data imbalance, I'm going to have it first off shuffle all the positives just to remove any like autocorrelation due to ordering. And then we're going to sample out so then we do a shuffle in the background to sample, and then we sample a subset of those. So I'm just sampling out 5,000 of the background as opposed to using them all. And then we concatenate those together and then shuffle again. So you can use this like sample frac, but set it equal to 100% is just a means to do a sample, right? So that's what this is doing. It's just shuffling stuff. So shuffle the positives, shuffle the background, subsample out only 5,000 chips from the background, merge the positive and the subsample of the background chips together, and then shuffle them again. There's probably an unnecessary amount of shuffling applied here, but it's good measure to try to keep things, not the data not so correlated. All right, so that's effectively how it generates a list of potential items to draw from. So we end up with this set one, which is our positive cases, and then a subset of our background cases. Okay, and then in the get item, this is how it's actually going to create a sample, right? So each individual sample or chip mask combination that it draws from. Okay, so from our created data set, we're going to grab the feature that's at a specific index. So this can be used for a loop. And then the second column, which has an index of 1, which gives the path to the image. And then the same thing for the mask, but we change the index here to 2, which is the path to the mask. And if you remember, again, if we go into one of these, the mask path is the second column, and the val is the third. And again, in Python, indexing starts at 0, so this is column 2 and column 3, right? Okay, and then once we have that, we read in the image. And here I'm using imread from CV2, so the computer vision library there. And then I do a conversion to change the band order, so blue, green, red to red, green, blue, because they're in a different order. And then I read in the mask, and I use imread unchanged because we just want to read it in as is. We make sure that each of those have the defined data type, so unsigned 8-bit. And then for the mask, we add a dimension, which is going to be the band dimension. Since it's grayscale, it by default just reads it in as a 2-dimensional array, but we want a 3-dimensional array, so we just add on a 3rd dimension on the end. Okay, so that's the get item step. And then dealing with transforms and other data manipulation. So right now, these are effectively NumPy arrays. So next thing we need to do is apply transforms, and we'll look at that in a minute. And then once we have that done, we're going to convert them into torch tensors, which we need if we're going to do deep learning on them. So going from NumPy array to torch tensors using the from NumPy method applied to those. Note that NumPy expects channels height width as opposed to height width channels. So this permute allows us to change the order so that the channels are first and then the height width as opposed to height width channels. And then it also expects it's going to want to have values instead of from 0 to 255, it's going to want values from 0 to 1. So we convert that data to float and we divide by 255 to rescale from 0 to 1. So same thing for the image and for the mask. Okay, and then yeah, so that's basically what happens there, and then ultimately it's going to return an image mask pair with those transformations applied, and then this last requirement is this length method, which will return the length there. Okay, and then for the seg data set, it's effectively the same, except I don't do the data subsetting. I just read in all the test and all the background and the positive. But other than that, it's effectively the same. Okay, so if we run those, that should allow us to load in our data. So let's hit run there. Let's hit enter, get this to finish up. Okay, and then the next thing we want to do is set some transformations. So for the test data, we don't need to do any data augmentations. So we just simply make sure that it has the correct height in widths and size. So I basically just set up some resizing. We don't actually need to do this at all because they all are or should be 256 by 256. So this shouldn't really change anything, but I did this for good measure just in case there was an issue with a couple of the chips and something weird with the size. Now for the training data though, we're going to want to actually do some data manipulation or data augmentation to try to reduce overfitting. And you can do different things, try different settings. Effectively what I'm doing here is I'm doing some random brightness contrast manipulation with some limits, some random horizontal flips, some random vertical flips, and some random blurs. The P relates to the likelihood of it actually applying that. So basically you have a chain of random image augmentations here to try to reduce overfitting. And these are all coming from the albumations library. That's the A here. So that's albumations. Note that Torch Vision has augmentations built in also, but I like this albumations package. I think is pretty easy to use. Okay, so we've defined our data sets and our transforms. And then we want to actually create those data sets, right? So I call my seg data train on with my train transforms, and my test data set with my test transforms. Oh, sorry, I didn't actually run these. I gotta run the transforms here. And then run this. Okay, and then I just have a print statement here to make sure it looks like what we'd expect. Okay, so I have 12,771 training samples. That makes sense because we selected 5,000 random, 5,000 random background, and there were 7,771 positive, right? And then there's our full validation set there. Okay, then once you have your data set defined, the next thing is to make a data loader. So the data loader is it's kind of confusing with what the difference is. The data loader basically works from a data set and it basically explains how to load in batches for training or validation, right? So we're using the torch utilities.data.data loader here. So for the training, we feed in our training data set, our train data set. We're going to feed a batch size of 10. We're going to have it do shuffling. We're not doing sampling. We're not doing batch sampling. I'm on a Windows machine where the number of workers doesn't really work well, so I'm setting that to 0. If you're on like a Linux machine, you should be able to fiddle with that, maybe get better performance. I'm not defining a collate function. Note that I could do the transforms in the collate function, and that actually might be faster than how I'm doing it, but I found that this worked fine. Okay, so the rest of these we don't really need to worry about. And then the test data loader is the same, except we're swapping out the test data set. You might be wondering what a good batch size is. Generally, I try to set it high enough that I'm not having a large number of batches, but small enough that it's not going to run out of memory. I found 10 worked on my machine. It'd be different for different computers and also for different chip sizes and number of bands and whatnot. Okay, so if we run those, then and there we go. So that read those. So now we have our data loaders defined. What this does is it's going to print some info about the data loaders to make sure. So we're just using this iterate next, and we're getting back a batch of images and associated labels or masks, and then we're just going to do some printing just to make sure things look reasonable. Okay, so we end up with a batch size of, or a image batch with dimensions of 10, 3, 256, 256. So the first dimension is the batch size, so there's 10 images. The second is the channels, so 3 channels, and then the height width, 256, 256. And the mask is basically the same, except 3 channels, it just has the 1, because it's just like a binary mask with 1 channel. And you can see that all of these are torch tensors, and they're both defined as float 32-bit. And here I pull out just one image from that batch and then print some information about this. Again, this isn't really required, this is just some tests. Okay, so alright, so again, for this image, it's a tensor of size 3 by 256 by 256, so 3 channels, 256 by 256 height width. It's float type. Mask is the same except 1 channel as opposed to 3, and the range for both is 0 to 1. So again, so each RGB band is scaled from 0 to 1, and then the mask is either 0 or 1, so background or mining. So that all looks good. We can also show them if you want. Note that if you're running this in a script file, it generally won't work. If you want to actually see them, you got to do it in like a markdown. So let me just open up I'm just going to make a markdown file real quick here. And let me just do this. So we'll run this, and then I'm going to make a Python chunk. And we'll just dump those 2 images into there. Okay. Okay, so one thing else you have to do here is you got to do plot.show to get it to print. And this is Matplotlib, if you're not familiar with Matplotlib. So we're going to do plot.show there. And the same thing here. Plot.show. Now if we run this, we should get our examples. All right, so there is our image. Oh, something didn't work. Oh, oops, this should be plot. Sorry, let me run that again. Okay, so there's our mask, and there's our associated image. You can see that this one had some type of transform applied, right? Because this is backwards, right? So it must have flipped it. And one thing to check is make sure that your mask and your images line up. So if you're doing like random flips or rotations or whatnot of the images, the same thing has to happen for the associated mask or they won't line up anymore. As this is written, it looks like it's doing that correctly though. Okay, so that looks good. Okay, so now we're going to actually set up a model. So in this example, instead of building a model from scratch, we're going to use some models from this library. So we're using go back up here, Segmentation Models PyTorch library, which I called in as SMP. So I need a semantic segmentation model, so I'm going to use a UNet. So it's going to be a UNet with the encoder that I specified above, so it's a ResNet 18. It's going to initiate on the image net weights, and it's going to have our classes. So it's just going to have the one class mining and the sigmoid activation function. So effectively that initiates the model. So if we run that, that'll generate a model object. Okay, and then we need to specify a loss function that will optimize against. So here I'm using a combination of dice loss and BCE loss. I'm just adding them together so they're equally weighted. Note that this BCE loss is effectively native to PyTorch, and this dice loss is something that's defined by the semantic model segmentation models library. So then we get our loss. These are metrics that we're going to print. All of these are coming from the segmentation models library. So we're going to calculate an F-score, an accuracy, recall, and precision on our test data set. Okay, and that's basic, so that'll call that in. Okay, and then we're going to use this Atom optimizer. I didn't set I didn't set I'm blanking. The learning rate. I'm just going to let it use the default, but you can set a learning rate inside of this argument. So that's just the optimizer. Then we need to define a training loop. Define a training epoch, so each iteration over the data. So in the training epoch, we're going to train the model. We're going to use our define loss function. We're going to report our metrics. We're going to use our optimizer. We're going to work from our device, which should be our GPU. And verbose means it's going to print some progress, right? And then the val loop is effectively the same. We just swapped out valid epoch, and that's it. So that's the only thing that we trained. Okay, so if you ran all this, you're really just defining what you're running. You haven't actually ran a model yet. To actually start running the model, we need to set up a training loop. So that's what this does. So for I in range 0 through 10, so basically we're going to run for run for 10 epochs. It's going to train the model. So we're going to do our train epoch using our training data loader, our test epoch using our test data loader, and then it's going to log some stuff, right? And specifically, it's only going to save the model to disk if there was an improvement in the F1 score in this case. And then if I is above 25 here, it's going to reduce the learning rate, but we are not actually using that because we only have 10 epochs. And at the end of the training loop, it's going to save out the best model. One thing else we could do here, which could be interesting, is at the end of each of these loops, we could recreate the training data loader so that it generates a new set of background samples. So we actually use more of our 10,000 samples, and all we'd have to do is just add in the data set, the segmentation training data set data set create function here, and then the associated data loader, and then it'll recreate that through each epoch. I didn't do that, but that's something you could do to potentially improve the model. Okay, so I'm going to run the model. This takes a while. I only did it for 10 epochs. You may want to do it for more. On my machine, I think it ran in 3 or 4 hours. You could run it for a lot longer and see if it gets better. Okay, so that's that. Next, we want to try to like validate the model. So I created a new data loader here that calls in the withheld validation set as opposed to the test and train data. As you see, it's actually pretty similar to it's basically the same thing as the test data loader. And I made a second version where it just calls in training. It just calls in the positives and not the negatives for later. So that's what that does. So, and then to actually validate the model, so once I call my validation data set here, then I create a validation data loader, set up a validation epoch, and then I can run it over top of that, and then it'll print out the assessment results. So that's how you can do an assessment on a data set that's not the test data that's being used at the end of each epoch. You can actually run it on a new set of data. Okay, and then lastly, we're going to run our model, and we're going to see what some output looks like. So I already ran this, and it got saved to a file. So I'm going to hit run here so it loads in that data. Oh, oops, this is I need to set the directory because I moved it. So that should be under, let's see here, it should be in the scripts folder. It's this model here. So let me just put it in this file path so it has it. And run. Okay, so now it called that model in. Okay, so now I'm just going to run these data loaders. Oops. Just because we will need them below. Okay, and then we'll create our val data loader there. And then again, if we wanted to do a validation, we could run it. This takes a while, so I'm not going to, but that would print out your recall, precision, accuracy, all of your validation metrics. Okay, so one thing we want to do once we have the model is just see what some of the output looks like. So here's a function to do that. So we set up some visualization of a visualize function and then run that on a subset of 10 data points or 10 chips. So let's look at what this is doing. So So n is the length of images, which is going to be your image input. So it's going to pull those. You set up a plot here that has certain dimensions, and then it iterates through those and then generates a plot with multiple axes. And then to actually get data, we need to first create the image. Remember that when we changed the band order, which to be channels first, which is what PyTorch wants, but Matplotlib is going to want channels last. So that's what this does. So permute 120 does that. And then I'm multiplying it by 255 to go from 0 to 1 scale to 0 to 255 scale. And I'm converting that into an integer. And then I'm just getting that data back as an image mask group. And then what squeeze does is that removes a dimension that we don't need. And then here we're unsqueezing, get back a dimension. Then we predict. So what this does, this is kind of confusing. This is a common issue that people run into. So whenever you do, so the way this is set up is it expects the tensors to be read into the model as batch channel height width. But since we're just reading it in one at a time, we have channel height width. So effectively unsqueeze 0 creates another dimension at the beginning of the batch, which is effectively just with the length of 1 that represents the batch dimension. And then to run the model, we just call the model name .predict, run it on the image tensor, and then we take our output and we just scale it so that we can use in Matplotlib here. So we take the mask, squeeze, send it from the GPU to the CPU, convert it to a NumPy, round it off. So instead of getting the probabilities, we get back zeros and ones, and then visualize those. All right, so let me run this. This may run in here. We'll see. Let me run here. So that should initiate our function. And now let's run it and see if we get output. If it doesn't, we'll just have to move it over to a document. There we go. Okay, it looks like it's going to print it. Okay, so here's some output. So we have our image. Let me make this a little bit bigger here. Move this a bit. All right, so we have our image. This was the actual mask, and then this is the predicted mask. And just looking at these look pretty good. So it looks like we're getting some reasonable results. All right, so that's that. So now we have a model, then we've trained it. We save the same model to disk. Now we want to actually use that model to infer to new data. Okay, so to do that, we want to open up our infer. So I'm going to open file and topo work and scripts, and then we want to open this infer function. Okay, so this is a little complicated, but I'm just going to step you through kind of what's going on here, and then we will look at some output. All right, so we call in the libraries that we need. We make sure our GPU is available. This is the same as the training script. We define a model and the loss function and the metrics and the optimizer, and then we load our model using the load function here. So basically that recreates our model and it loads in the weights that were learned. So that's our final trained model. Okay, so one thing that's kind of different from dealing with geospatial data versus other types of data is we don't really want to be able to predict back just to like one image chip as an individual unit. We'd like to predict back to a geographic extent. So generally what that means is we got to take a bunch of little chips, predict on top of them, and then merge them all back together to create a map extent. And that's what this function, this geoinfer function, does. So basically you give it an image. So this, in our case, is going to be a topo map. Then you name the output. You set a chip size. Generally, this should be the same chip size that the model was trained on. So I use 256 by 256 here. Stride X, stride Y. A crop. It's generally been shown that the margins of images tend to be more poorly predicted than the center, so I'm just going to crop off some of the margins, but use overlap, so we're mainly just using the center of each chip in our final model. And then the number of channels in the input, which in this case is 3. Okay, so what this does is it calls in the image, so here we're calling in the topo map, and then from that, we are saving it to as a NumPy, or sorry, as a tensor, a PyTorch tensor. And then I do the same thing here. I call the image again, but just pull the first band and set everything to 0. So this is going to basically create a blank or zeroed grid, or I guess tensor, with one band that we can write our predictions into that has the same height width as the image. I didn't just copy this, so you want these things to be delinked from each other. Okay, and then I give you something very similar to what I did with my chipit function. So it goes through and calculates the dimensions for the chips, the start and end points, and then it loops through all of those chips. Note that you do have an issue when you get to the end. So when you're at the end of a row or the end of a column, you might not have a full 256 by 256. So I basically wrote this so it'll kick it back so that it overlaps with the prior row or column and then stops perfectly at the end of the image. Okay, so then once that's done, it makes the prediction on each chip, and then it goes through and merges all those chips into the blank zeroed out grid, and it does different clipping or around the margins depending on where you're at in the chip. And then once that's done, I read in the image now not as an image but as a raster geospatial layer and pull the projection spatial reference information using rasterio and this profile function here. So I copy the profile, I make a couple changes to the profile. For example, the original image is 3 band but our output's 1 band. And then I write that output to a NumPy array unsigned 8-bit, and then write it out as a raster grid with the profile. So effectively it just takes an array and it assigns it back the spatial reference, coordinate system information associated with the original image, so it draws where it's supposed to. Okay, and then here I'm basically just going through that in a loop, and I'm looping through a set of rasters to get back a prediction. Okay, all right, so let's look at our actual prediction then. So I'm going to open up QGIS here, and we are going to look at some of our outputs. So this is the OFET quad. Actually, we may need a different quad. Let me, because I think that wasn't that. So we go into the predictions here, and let's just pick one. So let's look at, let's just look at this Barbersville one. Okay, I think zoom to layer. Okay, so this is a prediction for this Barbersville quad. So let's see what that looks like in comparison to the actual mass. So this is Barbersville. Okay, so there you can see those are pretty similar. A little bit different, but they look pretty similar. And then again, we can pull in the actual topo map. There we go. So let's just zoom in here, have a look. So here's a strip mine, mine extent area. So that's our topo map. This was the mask, the original image. And then this was the prediction. So you can see they're a little different, but overall it actually looks pretty clean. Okay. All right, and then the last step here is to do some model validation. So that's what this eval function is for. So that's the last of our scripts. We go File, Open File, and we want to open up our Eval Classification. And this is done in R, so we're moving back into R now. Okay, so I created this function called Eval Classification. It accepts reference data and predicted data, and then it creates a bunch of summary metrics for us. The way it's written is you can accept the reference data as a vector or as a raster, and the predicted data as a vector or a raster. Sorry, that's wrong. The predicted data has to be a raster. The reference data could be a vector or a raster. In this case, we're just going to use them both as rasters. Okay, so effectively what happens inside of this function is if it's a vector, it reads in, if the vector data or the reference data or vector reads it in, rasterizes it. If it's not, then it just reads them both in as rasters. Again, this is with the Terra package. It then from that stacks it into a single image with two bands. It does a cross tabulation on the two bands. And then from that cross tabulation or error matrix, it goes through and calculates some different metrics. And these are using different libraries in R. So things like, Caret, RF utilities, diff-R. So especially what I'm calculating here is an error matrix, and this is from Caret. From RF utilities, I calculate overall accuracies, and then error rates, allocation and quantity disagreement, and exchange and shift after Pontius. And then I merge all that into a list object and return the final list object. All right, and then this is just running that on one topo map, or you can run it as a in a loop on a set of topo maps. And then that's going to return back some of your statistics. So let's just run this on, let's see here. I'm going to do this. This would take a while. Let's just run it on the first one in the loop just so you can see what it does. Actually, we'll just do it this way. Okay, so hit run here. So this creates a list of topos, the validation topos that I had saved to a CSV file before. So we have the names, the mask names, the paths, everything. Now if we go in here to do eval, I'm just going to have it loop through, but I'm only going to have it do the first two. So here we do for I. Oh, actually, let's just have it do the first one just so we can see the output. So we want to run it here. We're going to run it on the first row. We're going to pull in the mask as the reference, and then our prediction from that we got out, and then it's going to be the truth data is going to be raster as opposed to vector, and then the code background is 0, not mining, and then our positive case is mining, which is useful for like precision and recall if you have like a binary classification. So let's hit run there. Oh, sorry, I have to create the function first. So let me set up the function here. Okay, and then we want to run that function. Want some data. Okay, so this is just going to run on one image. You can run it on a set of images if you wanted to validate over different areas. So like while that's running, I did this in the loop where I had to do all like 20 images, and it writes all those out into one data frame. So you have you can compare the results for different extents. Okay, need some warnings. That's okay. So our output should be called, should be called function test. So there you can see returned a list object here. So I'm just going to call that list object so we can see the output. All right, so here we have a error matrix. So this is your correct, not mining, correct mining, and this is was mining, called not mining. This was not mining, called mining. So our overall accuracy was basically 99.8%, kappa value of 94.7%. Here's our precision and recall. So recall was 95.3, precision 94.3, and then we have users and producers accuracies here, and allocation quantity disagreement, and it tells us what our positive case was and what our list of classes were. Okay, so that's effectively the whole process. So again, the goal here was to use an open source software stack, open source and or free software stack, basically R and Python, to prep data, train models, infer to new data, and assess model output for specifically semantic segmentation deep learning using a UNet on some topographic maps, which is raster geospatial data. So again, if you want to work through our directory, hopefully take a look at this video. You can play with these scripts and maybe manipulate them to do something that you want. And again, we're going to add some other examples using different use cases and different data sets and classes and problems.